And so today we want to talk about our ongoing research project, which is called From Manual Mapping to Automated Detection. And so we're going to talk about data sets. The aim of our research project is to develop a large, generic, and reliable learning dataset of labeled archaeological objects in LiDAR data. So in following, we will explain why we think we need such datasets, where we're going to get the data, and how we are trying to make it reliable. So why do we need a large learning dataset? For the last decade, archaeologists have started using machine learning and especially deep learning for detection of objects in remotely sensed data. I think we are by now all sort of used to convolutional neural networks and CNNs, and these seem very promising for this task of object detection. Most convolutional neural networks rely on a large data set in able to be trained. And when we talk about a large data set, I've made a little graph here of some of the well-known data sets and just put ImageNet there as well because it's so big. But as we can see, these data sets are tens to hundreds of thousands of images spread over tens of classes. Currently, we don't have any dataset comparable in archaeology. So instead of using just a large dataset to train, archaeologists have relied on transfer learning or domain adaptation. With transfer learning, we pre-train a neural network on a large generic dataset and then fine-tune or optimize our convolutional neural network on a smaller, more specific dataset. And this has been successful in several cases, as we have already seen today. However, this is not without problems, especially in object detection. For instance, the small specific dataset still needs quite some examples in order to properly transfer learn or optimize. And within deep learning, basically, most of the time it is the more data you have, you better. Also, the large generic dataset and the small specific dataset needs to be somewhat comparable. And we can wonder whether this very cute picture of cats and dogs is that comparable to LiDAR data. On the one hand, we have 3D objects in 2D images versus 2.5D surfaces that are visualized with the whole array of 2D visualizations. We have large and prominent objects that are generally reliably orientated. Most of the time, the dog is not upside down. Versus small and most of the time densely clustered but very scattered objects, for instance, as we can see with these barrows in this LiDAR image, that have almost a complete rotation invariance, so they can be orientated in any way. But maybe most importantly, we have on the one hand well-defined objects and classes versus much more ambiguous archaeological interpretations. And so Rolf and I were wondering whether it would be possible to make a dataset, a large training dataset for archaeology from LiDAR data. Such a dataset could either be used to pre-train a network or could be used as a source to supplement existing small datasets and extend those in order to improve the fine-tuning of a pre-trained network. And so where are we going to get this data? Because as we saw, we need tens of thousands of images. Well, luckily for us, one of us has been working on a huge dataset for years. And that's Rolf.
Thank you. Yes, for the past 10 years, I've been working on archaeological interpretation of LiDAR data for the whole state of Baden-Württemberg, which is one of the largest federal states of Germany. So there you have, oops, what did I do? So there you have a single person going through 22 square kilometers on average a day, mapping 700 objects per day, and running into all kinds of challenges from data management to processing quality to interpretation, all the time struggling with quite limited resources. So what's coming out of these 10 years of what I sometimes call stamp collecting is approaching 1 million mapped archaeological objects, most of which, as you can see, relate to resource exploitation and land use, field boundaries, rich and furrow, things like that. And as you can see, there's almost 30,000 charcoal burning platforms, and we'll come back to these in a minute. Of course, producing that amount of data, of archaeological data, has implications, greatly expands our knowledge of the archaeology. It underpins the shift of perception from discrete sites towards archaeological features embedded within archaeological landscapes. But there's two problems here. One is that there's essentially no quality control, neither a second pair of eyes looking at the data, nor field verification to speak of for that number of mapped objects. Another thing is that this 10-year mapping effort covered less than 1 per mil of the world's land surface. But I think that using neural networks and machine learning can help us with both of these issues. So what we want to do, the purpose of this is to develop a large and reliable labeled data set of archaeological relief objects. And we are starting with charcoal burning platforms because they're quite numerous, they're morphologically well-defined, and they're quite easily recognizable by humans, we think, forward. Later on, we want to add other classes of archaeological objects, such as hollow ways, burial mounds, things like that. So the content of the dataset will be tens of thousands of small LiDAR snippets with a size of 40 by 40 meter. There will be elevation data plus different LiDAR visualizations. And an important point here is that we want to add a quantitative measure of their recognizability by a human interpreter. Let's call it a recognizability score. One of the issues you run into when you want to do a data set like this is that LiDAR data can often not be freely distributed. So the way around in our case was that all geolocation information is removed from the data. We are not giving out absolute elevations, but relative elevations within the snippet. And all those snippets may be affected by arbitrary rotation. So doing this makes this data set essentially unusable for any other purposes than using this as a training data set, learning data set, while at the same time retaining all the information, everything that we need for just this purpose. So as I said, we want to have a quantitative measure of quality or recognizability. So what I did was I developed a very simple tagging software using VBA under Excel. It was only meant to be like a proof of concept. And then I decided, or we decided, to just leave it as that because Microsoft Excel is so widely available, and using this running this as an Excel macro makes it possible to run this on essentially any Windows PC, even where you're not allowed to install or execute any other software as a user. So what this does, it randomly shows a number of LiDAR visualizations. So the user has to click on the visualization which is best readable. Then the user has to decide how well he or she recognizes a given type of archaeological feature. In this case, for now, charcoal burning platforms. So this ranges from 0, certainly not, all the way up to 4, definitive. So then the user clicks on this, and the next random feature is shown. And I need a drink. Every feature can be shown several times to the same user. And the reason for doing this is that we want to have a measure for the reliability or stability of every user's interpretation. So we want to see whether the interpretation that the same user comes to the same interpretation on subsequent iterations. What am I doing? So let's look at some initial results. So you can see here, for now, there's 2 users who have together spent roughly 30 hours tagging around 55,000 objects. So for these 29,000 charcoal burning platforms, this means that on average, every object has been tagged twice. You can see that this is a rather fast process, but there's timing differences between the 2 users. User 2 is working quite a bit faster than user 1. But even if it's only 2 or 3 seconds per feature, if you're doing this for tens of thousands of features on several iterations, this really adds up. So it would be nice to find some volunteers to make this even faster. What am I doing? So what you can see here is a comparison of the tagging results for these two users. You can see that for user one, around 23%, I believe, of all the taggings fall into the two highest classes, while for user two, 48%, I believe, of all the taggings fall into the two highest classes. For both users, the middle class possible is the most common one. And what about the change from one iteration to the next for the interpretation stability? You can see here what you want to have is that there's a 100% circles all along the diagonal. You can see that there is quite a bit of scatter from one iteration to the next. You can see that interpretation stability varies from one user to another. For user one, the interpretations, the tagging results are more stable than for user two. Now, we can also do a cross comparison between users. Again, you want to have a complete correspondence. You would expect, if everything was ideal, to have 100% circles along the diagonal. You can see here that, for example, for the highest class, for definitive, 70.7% of the features tagged in this class by user one are also tagged like this for user two. You can also see that user two tends towards higher values, and in the end, when we put together the results, we will of course have to correct for all those differences. So what we can see here as initial results is that user interpretations are not stable, but that users interpretation stability can be quantified and compared. And we can also see that there's significant differences between users. So when working with large remote sensing datasets, this already shows us that it would be desirable to have multiple users going through the data in multiple iterations. And this takes us back to my 10 years mapping effort in Baden-Württemberg. This is the first time I have quantitative data on how arbitrary or ambiguous my results are. And this probably also has implications for any other large-scale single interpreter, single iteration mapping projects. Yeah, that's what it says. So to conclude, doing this work, yeah, I can do it in 2 minutes, gives us the opportunity to use the results from my large area mapping efforts to create a large generic data set of labeled archaeological objects for machine learning purposes. Now the steps ahead will be to continue tagging, and it would be nice to have some help there. We want to expand it to more classes of objects like burial mounds, etc. And then to consolidate the data set and distribute it. So what we will have in the end, hopefully, will be such a data set that we talked about, that Walter said in the beginning. That's what we want to have. So, of course, contributions in terms of time for tagging or even data donations maybe are very welcome. And otherwise, thank you.